And here it is. This is our working monitor and the app. What can we see? We have 3 screens. The first screen is showing our voltage, state of charge, that we are connected to the server, our amperage, and the watts minus means we are charging. With our button we can access the page 2 and 3. We have battery temperature and inverter temperature, the cycles, and how many watt hours in this cycle we have already charged. This is only for charging. Then we have our timer, since we have started the controller the last time, and how many disconnects of the Blink server or internet have been registered. All this, or most of it, we can also see on our app. So this is it. This is completing the software for our project. 6.3, 6.2, 6.28, 6.32, 6.24. So we are very close. Sometimes you can see outliers, but overall, in average, of course, for what we use it is quite accurate. Much more accurate than this one, because this one does only tell full numbers. And the voltage, same thing. My multimeter only have 1 digit behind the comma, and we even have 2 on the monitor. Here it finally is. This is the sketch for the battery monitor in version 1.0. It is already a very well tested sketch. I have run this now for about 1 week. So we are starting with our libraries, of course. There's a few standard, a few from Adafruit and a Blink, and then also some private ones. How do you get your libraries? You go to Sketch, you go Include Library, Manage Library, and there you search for what you need. So let's search, for example, for the INA 219, and this will present you a few libraries. And I took this one from Mr. Wolfgang Ewald, and this one is really nice because they have so many things which you can set. Okay, so all this is installed. I also have a few of the libraries on my GitHub page, especially those which are difficult to find, like the ESP8266 library, which you need if you use the ASP Shield, the ESP01. The next is for the Blink server initiation. So you have your out, you have your SSID and your password for your Wi-Fi to put in there, and the ESP, which of the communication ports are you using. I'm using the serial 2 on my Mega, and all these others is just you take it as it is. If you have to change I2C address, you can do it here. Please first make your scan on your device to see if all the addresses are the same. Okay, then our global variables are coming, all which have here some explanations behind. You would have to change for your system, probably, like the battery capacity here. I have 8000 watt hours, and this is used then to calculate cycles and this kind of stuff. The calibration value for the voltage measurement, because the voltage divider is always unique. It depends on the resistors and on the tolerance of the resistors. So there might be the necessity to change in the last digits a little bit. You just take a multimeter which you have at home, and then you, when the system is idling, you just make those numbers be same. You can enter which shunt you have, then intervals, how many times and when you want to do something. Best is if you maybe keep all those intervals as they are, except the loop. If you want to measure faster, I have here 700 milliseconds to do one measurement loop. You could go down to 500 if you want to do that faster, or even a little bit slower if you want. Then you enter your pins, which pins are there for the temperature measurement and which one you use for the switch if you use one, and so on. So in the setup we are beginning with our EEPROM. So if you start your microcontroller the first time, use the EEPROM for the first time, then you can decide if you want to flash some cycles already onto it. Like I had found out that probably my pack has already 560 cycles, something like this, 70. So I have used the first opportunity to flash the number of cycles onto the EEPROM. So if you already have some data on the EEPROM, you can use the example sketch for the EEPROM for clearing the EEPROM, and then when you run the first time, here this sketch, then it will flash something onto it. So how do you do that? We have EEPROM data is stored in bytes, so if we have numbers more than 256, we need to use 2 bytes to store that. So we have a low byte and a high byte. And I have flashed the number 567, for example, on my EEPROM when I run this first time. So that would mean a low byte of 55 and a high byte of 2. So 2 times 256 and plus 55 is 567. Then we have here the initialization of the INA 219, and this is what I said. This library gives us a lot of choices. So we can set the sample mode. So how many times the sensor will sample the input before it gives you the measurement value. Right, so I have set 32. So 32 individual measurements will be done, averaged out, and then it will present you the result of that. You can change this from values between 2 and 128, but this is in bytes, so you can see these numbers here. You can use the numbers here which are put here at the back. Our mode is triggered. We tell the sensor when it shall measure, and it measures 1 time. And then we have a gain. For gain, we have also 4 choices, and you use that one which is closest to your shunt maximum output voltage, right? So my shunt is a 100 amp, 75 millivolts. So I used here the value 80. 80 would be the maximum millivolts in this gain. Then correction factor, if you kind of find out that your device is measuring always a little bit too high or always a little bit too low, you can set this here and it will be already automatically corrected. Okay, then we are doing LCDs and we already write something on the screen and defining our pins, what kind of modes they're in, if they are outputs or inputs. And in the between we always have to do watchdog recess. So this is external watchdog so we need to always send a reset signal to that watchdog, otherwise, especially during the setup routines when everything takes a little bit longer to establish internet connection, this kind of stuff, we always need to reset the watchdog in between. So this you can see here in the next part, this is now the establishing of Wi-Fi and the blink connection, and all these single steps are followed by a watchdog reset, because each of these steps can actually take quite long, sometimes 15 seconds up to 20 seconds, where the controller will basically don't do anything and just wait for the answer of the communication. Here our ADS, and that's more or less the startup. In the loop, as I said, you can define how long the loop shall be, how many times you want to call it. And what we are doing there is we are just checking timestamps and then either go into the measurements or do the Wi-Fi stuff, blink, transmissions, and that's already it. The measurements, I call that here mode, because I use this sketch actually a lot of it, of course, from my Powerwall. But in the mode also is quite simple. These are functions for going to measure current, voltage, then we calculate the state of charge, and we get the temperature probes. I have 3 pages now on my LCD screen. You could see that already on the video before. And then we have 2 subpages which will cycle from one to the other all the time, as long as you push the push button. And that's it already. Then we have our functions. We have functions to reset the watchdog, to restart blink if it disconnects. Then our transmission. Here we can see we have our virtual pins, and this one need to match then in our blink app. So we are using 9 variables which are transmitted to the blink server. The temperature probes, we are reading 2 pins, analog pins, and calculating the temperature in Celsius here. Okay, then current. For the current, we are getting our measurements from our INA 219 sensor, of course. It's a value in millivolts, and that one we calculate to be amps. In this case, actually, every loop we are taking a measurement, but after every 7 loops, these measurements will be presented as a result. From the 7 measurements, we are taking the minimum and the maximum measurement extra, calculating the average current first of all the measurements, and then I'm removing the minimum and the maximum current because they could be outliers, right? And then we're checking how far are those 2 outliers away from the average. If they are close to the average, I put them together in the basket again, and we make a total average of 7. If one of them is quite far out, we do a little bit extra math here, and I'm taking that one which is closer to the average, giving them more weight, and then we put them back into the basket like that and calculate a new average. So after we have sorted the data by statistics a little bit, now comes a digital filter. We are using the moving average filter here. So we take the 5 most recent average readings. There are several examples of this in the internet. You can maybe get some further information if you're interested. Before, the buffer of the moving average is not yet filled. We're just showing all the actual current readouts, and then once the buffer is full, then we calculate the moving average from reading to reading. And then I have this indicator here. Whenever the actual current reading is more than 3% off from the last current reading, this would give some sort of indication. This will be nothing unusual. It will happen right when you start the monitor. Then of course there's no data in the moving average buffer, and later on, let's say the amperage values are changing very rapidly because of cloudy sky or something like this. This would also indicate that something is going on with the data, and that the data is really very dynamic at the moment. For the voltage, it's kind of the same principle. We are measuring every loop, but after 7 measurements again, there will be shown an average on the screen. For the cycles, so basically after every time we get our final current and voltage results, so that means after every 7 individual measurements, we are taking the watt number there, and if that watts is below 0, which means we are charging the battery, then we put that into the basket, right? So we are only counting watts going into the battery. Every 10 minutes we take the basket, divide them by the number of counts, how many times we have come into this sequence here, and we calculate the watt hours for this period, right? And once you reach the watt hours of your battery capacity, then this is counting as one full cycle. So in my case, I have 8000 watt hours. So every time we have watt hours to count, which went into the battery, we put them into the basket, and once we fill up to 8000 watt hours, the cycles will go up by 1, and this new value will also be immediately stored into the EEPROM. So the next time, if you would reset your monitor, it would be stored in the EEPROM. Okay, then the last part is already how to get the state of charge. For the state of charge, the first part here, we have to tell how much effect does current have on voltage. Because our voltage curve, which is here, that's the idle curve. So if we are charging or discharging, that will raise or sink the voltage. So this we have to calculate back to a certain idle voltage, and then we can go into the table and choose the corresponding number and tell, okay, this is this state of charge. It's quite simple and effective. For this chemistry, it is quite an easy task because the voltage curve is steep enough so that we can always follow it by just measuring voltage.
So for the code, you can find it on my GitHub page. Just follow the link below the video. That was it so far. We are almost at the end of our journey. There will be one more video just to conclude all of this, because now this is a passive monitor, but there could be of course also some active features included. So maybe you have also some ideas of what you would like to do with this kind of device. So please leave your comments. Thank you for watching this episode. Please give me a thumbs up if you like the video, subscribe to the channel, and I see you next time.